So we have most of these things are now in the symbolic form, except for the cumbersome 0.25 and 0.5 instead of the half and 1/4. This is because we have a gravity term which has not been given in a symbolic form. So by changing the gravity to g and adding another component g over here, and giving it a proper value, we can come back, rebuild the equations, and have a very neat expression for the three matrices which we are going to compare. The next step is to now actually verify if these matrices are accurate. So we bring in our Lagrangian modeling. We attach a Lagrangian modeling file which has been created in a previous video. Rerun the whole file. And we can find out the XM, VF and XC matrices from there on. We can just copy them here instead of XM. Substitute for theta 2, theta 1 and theta 4 as we have in the other matrices above, and find the difference of their two. So this indicates that we have a very proper matrix, and it is exactly the same in MapleSim as well as the Lagrangian formulation that we have derived earlier. We can do a similar sort of thing with the VF matrix. So we can copy it, delete this, paste, use the replacements and add them. So the VF is also accurate. The last thing to do is to actually use the XC, which is the constraint matrix, and take it onto the MapleSim file. However, now what we observe is XC is actually a very complicated sort of equation if you check the MapleSim file. This is because it is expressed in a reference frame at the breakaway point. That is this reference frame right here. So you can see that we have a minus L2 component which has been sort of deleted. This is because it has been broken away at the breakaway point, and this is the reference frame in which all the constraints are expressed. So the next step would be to actually find the rotation matrix which relates this reference frame to the base reference frame and convert all the constraints expressed in this reference frame to this particular reference frame, and then compare the two. So for that we use the getFrame function. So we use the file getFrameMotion function. We find the rotation matrix capital R of link to RBF2 frame B, which is nothing but the breakaway point. So we have link to RBF2 frame B, and if we say enter, we have this particular matrix. So we invert that matrix and multiply the constraints in the MapleSim file, which is stored in file XC, with this matrix to find out the constraints in the base reference frame. And next we find the difference of these two. The last two components are zeros, but as we can see, most of the components are not zeros. This is because MapleSim has simplified the position constraints, and it is very easy to see here that minus L1 sin theta 1 minus L2 sin of theta 1 plus theta 2 plus these two components is actually 0 because this is a position constraint. We can find out the position constraints by using file getPostCons command and then substitute directly these equations equal to 0 in this entire matrix. So doing that, we get all zeros. This implies that although MapleSim has expressed the constraint matrix in a different reference frame and also used the position level constraints in the system to simplify the entire constraint matrix, it is essentially the same thing which we find out using our regular method. So using this, we have proved that MapleSim not only allows us for easy simulation of the entire system, but also allows us to sort of get the underlying equations very easily and effectively. And we can also find the equations using multiple variations very quickly, which is absolutely not possible when we are using hand-coded equations. Thank you.